non-conservative force acting on it, so we have to figure out what is the work done by that, because I know that the non-conservative work is equal to the change in total energy. Work is force times the non-conservative force times displacement, which is equal to E final minus E initial. What is the work done by the normal force?
I'm still writing this down.
Okay, apparently people are waiting to spring the answer on me. We have a dot product between the normal force and the displacement.
What's delta E in this case again?
Change in energy. How do you do dot products?
Is it the flow method? I can't quite remember how to do dot products, but would you do the flow method, or is that
The what method?
FOIL?
You could, but ultimately we'd still be stuck with what is the essence of a dot product?
So parallel?
Yes. So if I'm multiplying the normal force times the displacement, what would the dot product be?
Positive. If it's parallel, right?
Is the normal force parallel to the displacement?
No, it's actually negative because I'm pretty sure it's perpendicular. I don't know.
It is perpendicular, therefore,
It's negative.
no.
It's a cross product.
It's 0.
Zero.
Wow. Okay, whatever. Oh, it's literally right there. I literally have.
None of the normal force is not helping it move down the ramp at all. It's not hurting the movement. The normal force is doing no work on it, so this is 0. So even though we have non-conservative work involved, strike that. Even though we have a non-conservative force involved, it's not doing any work, and therefore energy is still conserved. So ultimately, we have energy initial is equal to energy final, which is the same place that we were and will be on so many problems. So I have my initial kinetic plus my initial potential energy is equal to my final kinetic energy plus my final potential energy.
Because the way that flow force works.
You've done it once before. I'm prepared to be dazzled. What's the formula for kinetic energy?
Oh, 1/2 mv squared.
That was less dazzling than the last time.
You know what, Mr.
What's the formula for potential energy?
It depends on what you're asking. That's
Okay.
what she told me. That's exactly what she told me to say.
No, actually what I told you to say is which one.
Oh, sorry.
Whatever.
Which one? Which one?
What class are you in? All right. Since our conservative force is weight, what is the potential energy formula associated with weight?
mgh plus c.
And then the same stuff except final.
Do we have to put plus C?
No.
Not necessarily.
Okay, so what can we get rid of?
We can get rid of the mgh, right?
Both of them?
No, I lied, sorry. I forgot. It's initial. Can we get rid of c? We can get rid of mass.
We can get rid of MGHF because H would be 0
Why?
because at the bottom.
Oh, that's not why.
Wait, what did you say?
I said we could get rid of MGH.
She's saying that's 0. And I asked why. And she said because it's at the bottom. And I said that's not the reason why.
Because because
MGH
it's like it's at the initial thing. So wait, why is she wrong? It makes sense.
I
What
didn't say
is
she
that?
was wrong, I just asked why. Oh, I was
Oh.
saying she was wrong about why it's 0 at the bottom.
No, I know. I'm saying wait, why is she wrong? Because if it's at the bottom, that means it's where like the initial position is. No.
Well, not the initial position, but
Like it's next to this. It's like on the same thing as the starting point. Is what I'm saying.
no,
Like,
it's
We're
or
talking
the
final.
origin. You know what I mean?
I can guess, but not 100% sure.
So the
We're
bottom.
talking about down here,
Yeah.
and it's near, it's not near the starting point because that's up there. You're saying it's near the origin?
Oh, I'm sorry. I was forget about it. I was choosing the starting point as the bottom. You know what I mean? Like I'm saying, you know.
So you're wanting, you basically set up a coordinate system where that's
Yeah.
crosses here?
Mhm. Listen,
Is that wrong?
I don't know.
Why is it not wrong?
Well, because if you have like
I said my
an
bad.
origin of some sort at that point, then it would be correct.
But Erica?
Would it be 0 because it's not moving? And it's
Who?
staying in one?
That's not the reason why H final is 0 or why that's the origin.
Wait, why? Oh, so that is the origin. So that can't.
I
be-
don't know if it is or
I
not.
feel like it could be the origin. Because
Why?
Can we take out 1/2 now
Because
that
I said so.
There we go.
Yeah.
All
That's
right.
the answer. Because I said so.
Why is H final equal to 0?
Because I said so.
No.
Because Stephanie said so. Because Stephanie said so.
Yes.
Makes sense.
See, that's exactly.
We can make H final, or we can make H is equal to 0 wherever we want. That's the advantage of this plus C's. It allows us to shift everything. So you can set up some sort of axis here, but you can make 0 wherever you want, which is very convenient. So,
0's the bottom or the top of the round?
H is equal to 0 here, and the reason? Because Stephanie said so.
That's exactly what I'm trying to say the whole time.
Let's assume, for the sake of this, that it starts at rest. And so what our problem has now been reduced to is that G times the initial height is equal to 1/2 V final squared.
Yes.
Hold on, why didn't we take out GH on the left side if we took out GH on the right?
We took out GH on the right because we're defining our height to be 0 there. Yes.
Because he
It's
said
Stephanie's
starting
fault.
at rest. Because he said so.
So the speed at the bottom is equal to the square root of 2GH, the initial, which is the square root of 2 times 9.8.
Can we take out 1/2 now that we don't have?
No.
Okay.
I multiplied both sides by 2 to get this far, get from here to here. What is my initial height?
10
Yes.
meters. And then, does anyone know what the square root of 196 is?
Is that 14
Yeah, 14.
units?
Meters per second.
If we were using chapter 4, chapter 5 stuff, we'd have weight, we'd break it up into its components, figure out the component down the ramp. We'd have to figure out how far it's going down the ramp. Once you get used to this way is faster. However, at this point, the other way might seem faster. I'm about to make the problem look harder. Any questions?
No.
Oh, okay.
how fast is it going at the bottom? That's the ultimate question. How fast is it going at the bottom? Let's assume frictionless.
So it's, okay.
So obviously, normal force is changing directions in this case. We have weight and normal force still acting on it, but at any point, so let's say we are here, that does not work on the board. We are here. The normal force is acting up and the weight is acting down. So that's my weight and that's my normal force. At this point right here, the normal force is acting at an angle and weight is acting down. But if we look at the dot product between the normal force and the displacement, you're traveling along the surface here. The normal force is perpendicular to the surface at any point. So your displacement at any point on this path, your displacement and the normal force at that instant are perpendicular to each other. Therefore, it is still got energy is still conserved.
Okay.
So, what's the answer to the problem?
14 meters per second.
Yes. Nothing has changed other than the landscape. If we threw friction into it, that becomes more complicated. But in a frictionless situation, it doesn't. There's no problem there. Questions before I make it look more difficult? All right. I was going to put a spring in.
Please don't put a loop loop.
For town. How fast is it going at the bottom? Yeah. All right, let's make it.
I noticed it's kind of like a sine graph, but at an angle. Are we gonna do that?
It's like a sine graph, but at an angle. That's just coincidence.
No,
Okay.
that's not.
Let me draw moguls on my slopes. All right, so now we're going to put a spring at the bottom. Because why not? I do need to give a mass of the object now. The mass is going to have some importance here. The ultimate question is how much will the spring compress? So let's make the mass 50 kilograms. Now, how much the spring compresses also depends upon how stiff is the spring. First off, it's ideal. Because it's an ideal spring, it's not going to interfere with itself. With the slinky, and there was one in here, and is there still one? Ah, there it is. Hidden in the game. So with a slinky, you know that it's only so far I can push it. It will interfere with itself. An
Okay,
ideal spring will not.
What is that squiggly line right before the loop loop?
Another loop to loop.
This one right here, that's
no,
an arrow.
No, the other one.
That?
Yeah.
It's an arrow.
This
I'm just pointing to that spot.
Why?
Because at that spot, those are the forces involved. In those
Oh, okay.
directions.
Excuse me?
No, I've seen Dr. Fox likes to be different with his arrows.
Okay.
I had a professor in college who did it that way so that you could differentiate between, say, force arrows and just pointing arrows. That's why I did it. It worked for me. And therefore, it works for everybody.
Yeah, exactly.
It's an ideal spring. Now, so it will exert a conservative force. We do need to know the stiffness of the spring, and so that is bundled up into what's known as the spring constant. So I have a lowercase k, which I will sometimes put a little loop in there. It's a lowercase k, and we'll make this 20 newtons per meter. And what that's telling us is that if I want to stretch or compress this spring 1 meter, it will take 20 newtons of force to do it. If I want to stretch it 2 meters, 40 newtons.
What's K again? The lowercase?
It is the spring constant. Sometimes referred to as the stiffness constant. The larger the number, the more force it takes in order to stretch or compress a spring. So it's a measure of how stiff.
And the lower one is also okay?
Yeah, it's just showing different
It's like
variations. Okay, it's not an
first
uppercase
K.
K.
Okay. And the two Ks are different?
No.
Just that I sometimes write one or the other K.
Okay.
The only non-conservative force involved is normal force. It does no work. Energy is conserved. So we have energy initial. And yes, I am about to ask that question again. Here we go. What's the formula for kinetic energy?
1/2 equals mv squared.
Done in rounds. Aren't you supposed to do that several times if you're really doing it in rounds?
1/2 mv
And then matching,
I don't know, I feel like I was
harmonizing, that's the word I was looking for. What's the formula for potential energy associated with the two conservative? When we reword that, what are the formulas for potential energy associated with the two conservative forces involved?
Oh, one of them is 1/2 K times change of, is that displacement or?
From equilibrium, delta x
And then square.
squared. That's the initial. And what's the other one? Plus constant 1
MGH.
mgh initial plus constant 2. And it's equal to the same thing except the finals. 1/2 mv final squared plus 1/2 k delta x final squared plus c1 plus mgh final plus c2. Obviously, constants go away.
Is the first, so we don't need to even write that?
No.
Okay.
And normally I don't. It's just that it was brought up a couple times, so why not? All right, what can we get rid of?
We can get rid of M, but it's
Nope.
it's not in every single thing. So.
There's no M in
Those.
the elastic potential energy.
I mean, we can get rid of the 1/2.
We could multiply everything by 2.
Yeah.
So the 1/2, there's a 2 there now, 1/2, that's a 2 there now. Okay.
Can we still get rid of 2 MGH final?
Why?
Because I said so.
Okay. From a pedantic point of view, we can get rid of it because H final is 0. H final is 0 because you said so. We can get rid of a couple more things. We can get rid of actually 3 more terms.
Yeah. Is VI, are we starting at rest here?
Yeah.
So then it's 0
All right.
at the beginning. So
Why did you cross out the last MGH?
Stephanie maybe.
Because you just decided it was equal to 0?
Yeah.
Okay.
Two more.
So
Well, why don't we write down what we've got so far, clean it up a little bit. So I have
what is it?
k delta x initial squared.
Is it? That's 0, right? thing that you're writing down right now?
This?
Yeah.
Ooh.
Isn't
That's what we're actually trying to find there. The question is how much will the spring compress? That's that.
Is the displacement initially 0?
Yeah, the spring's just sitting there.
Oh, I was looking at it as the object. I just switched. And we can still get rid of one more thing?
Yes.
Is it mass times final velocity squared?
Why is that 0? It's not because you said so.
I don't know. I feel
Because
like
it
it should
stopped
be
at
0.
rest?
Oh! Nothing.
Wait.
Well, is it because final velocity would be 0?
The question is how much will the spring compress? If it's still moving, if the mass is still moving, it hasn't finished compressing. Or we're past compression. But at that moment that it's fully compressed,
Velocity would be 0.
it would be 0.
So I was right?
Yes. All right. So what we're talking about here is we have all this gravitational potential energy and no kinetic. As it's going down the hill, there's some oscillating back and forth because there are various curves in there. But at the end, it's all kinetic energy. And then it hits the spring. When it hits the spring, the kinetic energy will drop and the potential energy will start to increase. So it starts out with all this gravitational potential, converts to kinetic, and then it converts into elastic potential.
So when you say the spring is sitting FD and H, what's that mean?
Fat, dumb, and happy.
Fat, dumb, and happy. Okay. So it's just sitting.
Yeah. I had a colleague years ago who kept using that expression. That's why it's stuck in my head. So we have now reduced the problem down to 2 terms. I know mass, I know g, I know initial height, I know k. Only thing I don't know is delta x.
So we solve for that?